This is Decoded, the video engineering podcast by Fora Soft. Episode 8, Entropy and the True Limits of Compression.
You know, I was just thinking about this specific moment we've basically all had sitting at a computer.
Oh, yeah. What's that?
Well, you have this massive folder, right? Like tons of text documents or spreadsheets, whatever. And you right-click, you hit compress, and suddenly this giant gigabyte of data just, it shrinks down to a fraction of its size.
Right. It feels like total software magic.
Exactly. But then you try to do the exact same thing with a raw 4K movie file. You zip it, the progress bar crawls across the screen,
and basically nothing happens.
Nothing happens. The file is basically the exact same size. And it leaves you wondering, why can't we just compress digital files infinitely? Like, what is the invisible mathematical wall that stops us from taking an entire 4K feature film and just squishing it down into a single kilobyte?
Yeah, that is the million-dollar question, isn't it?
It really is.
Yeah.
And the answer actually lies in an absolute boundary of physics, which is mapped out in our source material today. We're looking at Chapter 8 of this incredibly dense, fascinating technical book on information theory, entropy, and the Shannon limit in video compression.
It's a fantastic chapter, really foundational stuff.
It really is. Okay, let's unpack this. Because to understand how we shrink data on our phones or laptops or streaming services, we first have to, completely rewire our understanding of what the word information actually means.
Yeah, it requires a total paradigm shift. To get there, we have to look back to 1948 to this Bell Labs engineer named Claude Shannon.
The father of information theory.
Exactly. He published a single paper, A Mathematical Theory of Communication, and he functionally invented the science of information theory right then and there. And his core, his radical premise, was that information has absolutely nothing to do with meaning.
Wait, really? Nothing to do with meaning?
Nothing. To a computer, information is literally just a measure of surprise.
Which is, it feels completely counterintuitive at first.
Yeah.
Because I think, we associate information with learning something valuable.
Right, human meaning.
Yeah, but Shannon approached it purely from the perspective of statistical predictability. The source text gives a great baseline example for this. It says, if I send you a message that says, the sun will rise tomorrow morning, mathematically, I haven't given you any information at all.
None. Zero. You already knew the sun was going to rise. The probability of that event is 100% or 1. So because there is zero surprise, there is zero information.
But if I send you a message saying, it will snow in your city tomorrow, and you happen to live in Miami in July.
That message carries a massive amount of information.
Because it's a highly improbable event.
Exactly. Shannon formalized this concept. The less probable an event is, the more information a message reporting it actually carries.
It's exactly like watching a movie. If the plot follows every standard trope and the hero is going to defuse the bomb at the last possible second, your brain isn't receiving any new information.
Right, you're just watching the inevitable unfold.
But a massive, beautifully executed plot twist. That is a high information event. You never saw it coming, so the surprise registers as new data.
That's a great way to put it. And, Shannon needed to translate that conceptual feeling of surprise into a hard, calculable metric.
Something a machine could actually use.
Right. So he proposed a mathematical formula for what he called self-information, and he measured it in bits. And he specifically chose to use base 2 logarithms to calculate those bits, which is honestly a brilliant piece of engineering.
I want to pause on the logarithm part for a second, because the text makes a real point of explaining why we use logarithms instead of just, looking at raw probability fractions. And it solves a major physical problem with how we store data.
It does. It solves what we call the additive problem. So let's look at the underlying math. Probabilities are inherently multiplicative. If you flip a fair coin, the chance of heads is 1/2.
Okay, sure.
If you flip 2 independent coins, the probability of 2 heads is 1/2 times 1/2, which is 1/4.
Right. But when we think about storing that data on a hard drive, we don't want to say 2 coin flips take up 1/4 of a bit of space. That doesn't make any sense physically.
Not at all.
If 1 coin flip requires 1 bit of storage, 2 coin flips must require 2 bits of storage. We need the math to add, not multiply.
And that is the magic of the logarithm. Logarithms mathematically transform multiplication into addition.
Oh, right.
Yeah. So by running the probability through a base 2 log, that 1 in 4 chance cleanly outputs as exactly 2 bits of information. A fair die roll, which has a 1 in 6 chance, outputs as about 2.58 bits.
And what about a standard byte?
Well, a standard system with 256 equally likely values outputs exactly 8 bits. The math flawlessly aligns statistical surprise with physical computer storage.
Which sets up this really incredible pitfall mentioned in the source material. Because information is entirely divorced from meaning, right? It's tied strictly to statistical surprise. So a string of completely random garbage letters actually carries more bits of information than a beautifully crafted sentence of the exact same length.
It really does. The random letters are totally unpredictable, making them maximally surprising.
So for a machine trying to compress data, a Shakespearean sonnet is fundamentally less informative than a cat walking across a keyboard.
What's fascinating here is how we transition from evaluating a single event, like one keystroke, to analyzing an entire ongoing stream of data.
Okay, so zooming out.
Yeah, and this introduces the concept of entropy. If self-information is the surprise of a single event, entropy is the average surprise of an entire data source over time.
Got it.
The golden rule of entropy is distribution. If a data source spits out symbols with perfectly equal probability, the entropy is maximized. But if the data is highly skewed, meaning certain patterns or symbols appear much more frequently than others, the entropy drops.
Let's ground this with the text alphabet example, because this is the specific mechanism that makes compression possible in the first place. So we have two data sources, and they both only use a 4-letter alphabet: A, B, C, and D.
Right. Let's look at the first source. It outputs those 4 letters with perfectly even distribution. There is a 25% chance for an A, a 25% chance for a B, and so on.
Very predictable. I mean, unpredictable, evenly unpredictable.
Exactly. If we run that through Shannon's average surprise formula, the entropy is exactly 2 bits per symbol.
That tracks. 4 equally likely options require a standard 2-bit binary code. But the second source uses the exact same 4 letters, yet it's skewed. It spits out strings that look like A, A, B, B, C, D.
Right. In that second source, the letter A is appearing 50% of the time, B shows up 25% of the time, and C and D only appear 12.5% of the time each.
Heavily skewed.
Very. Because the stream is far more predictable, I mean, you can safely bet that half the time the next letter will be an A, the average mathematical surprise drops. The entropy of this skewed source falls from 2 bits to just 1.75 bits per symbol.
Hold on, though. I want to look at the physical reality of this just to play devil's advocate for the listener.
Sure, go for it.
In both of those scenarios, if the document is 1,000 characters long, it's still physically 1,000 characters.
Yeah.
Just because I mathematically know A is going to show up half the time doesn't magically erase the letters from the page.
Right.
So how does knowing this statistical skew actually translate into saving 12.5% of my hard drive space?
You save the space by abandoning fixed-length codes and moving to variable-length codes.
Okay, explain that.
Normally, a computer gives every letter a standard 2-bit code. A is 00, B is 01, C is 10, D is 11.
Yeah.
But we know A is doing 50% of the heavy lifting in our skewed file.
Right.
So we dynamically rewrite the rulebook. We assign the letter A an ultra-short 1-bit code, maybe just a 0.
Oh, wait, this is the exact same underlying logic as Morse code.
Yes, exactly.
The letter E is the most commonly used letter in the English language, so telegraph operators made its code a single fast dot. But a rare letter, like Q, gets a long, complex dash, dash, dot, dash. You are saving time and space by handing out the shortest codes to the most frequent visitors.
It is the exact same logic applied to binary. A gets a 1-bit code, B gets a 2-bit code, and those rare C's and D's get longer 3-bit codes.
So when you pack it all together...
Right. When you pack all those ones and E's sequentially onto a hard drive, the massive number of ultra-short A's drastically shrinks the overall physical length of the file. The average length of the code flawlessly matches that 1.75 bits of entropy. You have just losslessly compressed a file by 12.5% without dropping a single letter.
That is wild. But, okay, if variable length codes let us exploit skewed data to save space, the natural progression is to ask, where's the bottom?
The floor.
Yeah. Can we just keep rewriting the rulebook, finding deeper skews and shrinking the file indefinitely?
We cannot. And that brings us to Shannon's source coding theorem. He proved mathematically that a data stream's entropy is the absolute hard floor of lossless compression.
So it's a physical limit.
It is a physical limit. You can design an infinitely clever algorithm to get closer and closer to that entropy number, but you can never drop below it. The moment you try to compress a file smaller than its inherent entropy, the math breaks down and you permanently lose data.
Source uses a brilliant analogy for this that really crystallizes the concept. Imagine your data as the physical metal key to a locked safe.
I love this analogy.
It's so good. That key has a highly specific, jagged physical shape. That shape represents the entropy, the absolute bare minimum structural information required to open the safe. Now, you can take the paper envelope holding that key and fold it up as cleverly and tightly as you want to save space in your pocket.
But you can't fold the key.
Exactly. No matter how good your origami skills are, you can never shrink the physical metal key itself.
The envelope is your compression algorithm, and the key is the entropy. And over the decades, computer scientists have essentially perfected the origami. In 1952, David Huffman invented Huffman coding, which builds a mathematical tree to assign those variable length codes we just talked about.
Right.
It's incredibly efficient, but it has a limitation. It has to use whole bits. If the math says a symbol's entropy is 1.3 bits, Huffman coding is forced to round up and give it a 2-bit code, which ends up wasting 0.7 bits of space.
But the text notes, we eventually solved that whole bit limitation.
Yeah.
With arithmetic coding.
We did. Arithmetic coding is just an absolute masterpiece of mathematics. Instead of giving individual codes to individual letters, it maps the entire data stream, no matter how long, to a single floating point number between 0 and 1.
Oh, wow.
Yeah, and as it reads each new letter, it mathematically narrows down that fraction on a number line. Because it operates on a continuous number line rather than discrete whole bits, it bypasses the rounding problem entirely.
So it's insanely precise.
Oh, incredibly. Modern arithmetic coding hugs Shannon's theoretical entropy floor to within fractions of a percent.
So what does this all mean for our daily interactions with technology? Like, for you listening to this deep dive right now, when you zip a folder of text documents and it shrinks down to a quarter of its size, you aren't witnessing a software miracle.
Not at all.
You are just watching arithmetic coding perfectly fold the envelope down to the natural entropy limit of human language. It stops shrinking because it physically hit the mathematical floor.
Which naturally leads us to a massive misconception in the tech industry regarding video. We constantly see headlines about revolutionary new video codecs.
Oh yeah, all the...
The industry moved from H.264 to HEVC, then to AV1, and now to things like VVC. And every single time, the marketing heavily emphasizes that the new codec, compresses data 50% better than the last generation.
But based on everything we just established, that shouldn't be possible. I mean, if arithmetic coding already solved the envelope folding problem and hit the lossless entropy floor decades ago, how are VVC and AV1 shrinking files so much further?
It's a great question.
They can't possibly have a better entropy coder that breaks Shannon's laws. So if the final compression stage hasn't fundamentally changed, the heavy lifting must be happening before the data even reaches the entropy coder, right? Like, they must be artificially manipulating the data to lower its entropy first.
Your deduction is spot on. Newer codecs do not have magically better entropy coders. They just have vastly superior prediction algorithms that meticulously prep the signal.
Or the signal, okay.
Let's look at the text running example. The Foreman clip. It's a standard engineering test video showing a man in a hard hat talking to the camera.
I think I've seen that one.
Yeah, it's a classic. The raw, uncompressed 4K data for that video requires 36.5 megabits per second of bandwidth. When you run it through a standard H.264 codec, it outputs at just 0.3 megabits per second.
Okay, 36.5 down to 0.3. That is a 120-to-1 reduction in file size. But wait, if the lossless entropy coding is already maxed out, what percentage of that 120-to-1 drop is actually coming from the entropy stage?
Just a factor of 2.
Wait, only a 2-to-1 reduction from the actual compression stage?
Yep.
So where on earth is the other 118 times reduction coming from?
It comes entirely from stripping out spatial and temporal redundancy.
What does that mean?
Well, a modern codec doesn't look at a video as a sequence of independent pictures. It looks for patterns it can predict. Through a process called block matching, it divides the screen into a grid. If it sees the background isn't moving, it doesn't waste space redrawing those pixels in the next frame.
Oh, it just keeps them the same.
Right. It just generates a motion vector, a tiny mathematical instruction that basically says, take this block of pixels from frame 1 and just copy it over to frame 2.
Oh. So it's actively synthesizing the next frame based on what it already knows.
Yes. The codec generates a highly accurate prediction of what the next frame should look like. Then it subtracts that predicted frame from the actual raw frame. The difference between the two is called the residual.
Okay, the residual.
And if the codec's prediction was really good, the residual is almost entirely zeros. There are only a few tiny numbers where the prediction was slightly off.
And connecting this back to the AAB example from earlier, a data stream that is almost entirely zeros is insanely skewed.
Massively skewed.
You've taken a chaotic, high-entropy stream of raw color data and mathematically forced it to become a highly predictable stream of mostly zeros. You artificially tanked the entropy, which allows the arithmetic coder at the very end of the pipeline to shrink it down to almost nothing.
Exactly. The 118 times reduction is all about getting better at predicting the video so the residual hits 0 more often.
That is so clever.
It is. But to achieve a 120-to-1 compression ratio, you eventually hit a wall where even the best lossless prediction isn't enough. You have to transition to lossy coding.
Throwing data away.
Right. You deliberately throw away high-frequency visual data like, say, the microscopic texture of the asphalt in the background, knowing the human eye won't even notice it's gone.
Which raises the ultimate question. If Shannon's 1948 paper calculated the absolute floor for lossless compression, did he define a mathematical floor for lossy compression too? Or is it just the Wild West once we start throwing pixels away?
If we connect this to the bigger picture, Shannon anticipated this exact problem.
Of course he did.
In a follow-up paper in 1959, he introduced the rate distortion function, or the RD curve. This defines the absolute theoretical limit of lossy compression.
The rate distortion curve, so rate representing the bitrate or the file size, and distortion representing how degraded or blurry the video becomes because of the data we threw away.
Correct. It maps the fundamental trade-off. If you plot it on a graph, on the far right side you have maximum distortion, a terrible blocky video, but the curve shows it requires almost 0 bits to transmit.
Right. A terrible quality, tiny file.
As you move to the left, demanding less and less distortion, the curve rises steeply, demanding more and more bits. And when you reach the far left, edge 0 distortion, meaning a mathematically perfect reconstruction, the lossy curve seamlessly merges with the lossless entropy floor.
So they are literally two halves of the same physical law.
Exactly.
But the source material warns against a very specific trap here. Engineers constantly ask, what is the definitive Shannon limit for video? And the text points out that this is a fundamentally flawed question, right? The limit cannot be a single number.
It can't be a single number because the RD limit is a dynamic curve and its exact shape shifts based on 3 distinct dependencies.
Okay, what are they?
First, it depends entirely on the source material. The RD curve for a static, calm portrait of a person is vastly lower than the curve for a chaotic, sweeping camera pan across a crowded football stadium.
Because the football stadium has drastically more inherent mathematical surprise.
Precisely. Second, the curve depends on the statistical model the codec uses to interpret the video. And third, and most importantly, it depends on the specific mathematical metric you use to define distortion.
Like how you measure the blurriness.
Yeah. Are you using something like mean squared error or MSE, which strictly calculates the raw pixel-by-pixel mathematical differences? Or are you using VMAF, a metric developed by Netflix that models subjective human perception? Changing the distortion metric literally redraws the floor on the graph.
But regardless of where the specific curve sits for a given video, the underlying law remains. You cannot encode a video below that line. It is the bedrock of the digital universe.
Absolutely.
And according to the text, we're basically standing on it right now.
Right.
By the 2025-2026 timeframe, modern codecs like VDC and AV2 have pushed their efficiency so far down that they're within a few percentage points of the theoretical lossy floor, at least one measured by classical metrics like peak signal-to-noise ratio or PSNR.
Yeah, we have effectively exhausted the mathematical headroom for traditional video compression.
It is a profound testament to Claude Shannon's genius. I mean, in just 2 papers, published before the integrated circuit was even commercialized, he flawlessly mapped the outer boundaries of the internet and modern streaming decades before they existed.
It really is mind-blowing. On one end, you have the lossless entropy floor dictated by data surprise, and on the other, the lossy rate distortion curve dictated by quality trade-offs.
It fundamentally changes how you look at the devices we use every day. You know, every time you zip a file, load an image, or stream a deep dive like this one, you're interacting directly with Shannon's laws. But here's where it gets really interesting.
Oh, where does it go from here?
The text leaves us with a pretty provocative look at the frontier. We just established that codecs have hit the floor when using classical pixel-based mathematical metrics. We can't squeeze the pure math any tighter. So the cutting edge of compression is abandoning pure math entirely and shifting to artificial intelligence, to neural codecs, and perceptual metrics.
Because human biology is flawed. We don't see the world as a grid of pure mathematical pixels.
Exactly. We have blind spots.
Yeah.
So what happens when AI starts defining distortion not by which pixels are mathematically incorrect, but by human psychology.
Oh, wow.
What if an AI codec decides to completely throw away the complex data for, say, a brick wall in the background of a movie, and instead the AI on your TV just hallucinates a brand new brick wall over the empty space in real time?
Mathematically, if you check the mean squared error, that's a disaster. It is a massive distortion from the original file.
But to your human eye, it looks perfectly sharp, textured, and real.
That completely subverts the traditional rate distortion curve. You are no longer compressing data, you are transmitting a prompt and synthesizing reality based on human visual blind spots.
Right. So will the Shannon limit of the future even be based on data physics? Or will it be based on how easily the human brain can be tricked? If compression becomes entirely about what we think we see, rather than preserving the true data, what does the word lossless even mean anymore?
That is a terrifying and fascinating thought.
Does the exact physical shape of the safe key even matter if an AI can just build you a completely new safe that looks close enough? It's definitely something to mull over the next time you compress a file, stream a movie, and wonder just how much of the original reality is actually left on your screen. Thank you for joining us on this deep dive. Keep questioning the digital world around you.
That was Decoded, the video engineering podcast by Fora Soft. Thanks for listening, and see you in the next episode.